Section 1.5. In this section, we will look at the solution sets of homogeneous and non-homogeneous linear systems. If we recall from a previous section, we saw that a homogeneous linear system is one that is made up where the constant term is the zero vector. So we always have zeros here. Now we'll see that this linear system is always consistent. Why is this the case? Regardless of whatever our matrix A is, we notice that the x is equal to the zero vector is always a solution to this system. And we call this a solution the trivial solution. If the zero vector is not the only solution to the system, then the homogeneous linear system has infinitely many solutions. We call this the non-trivial solution. So when looking at the solution to a homogeneous linear system, we want to know one of these two questions. Is the solution unique? Which means we only have the trivial solution? Or are there infinitely many solutions? Which means that we have a non-trivial solution. So let's look at an example. We look at this system here and we want to know, does it have a non-trivial solution? And that just means, are there infinitely many solutions to this system? Putting this system into an augmented matrix and performing EROs, we get to an equivalent system that looks like this. And we notice that it indeed has a non-trivial solution. So we can say, yes, this system does have a non-trivial system. Notice when performing the EROs that the B will always be, if we notice here, will always be 0 as we continue here, will be the zero vector. So in actuality, we can just look at the coefficient matrix when we have a homogeneous linear system. Let's look at what the solution to this system looks like. Looking at the coefficient matrix, we see that our solution will be x1 is equal to 1/2 x2, and x2 is our free variable. Now, if we let x2 equal to a, any real number, then if we write our solution set in this form here, the vector x is equal to 1/2 a and a. Or we can see it written as a linear, as an ordered pair. Since a is any real number, we can actually take this constant out and we have a times 1/2 and 1. So a times the vector 1/2, 1. Writing our equations in this form, we call this parametric vector form. Now let's think about what the geometric interpretation of this solution means. So I have x, the x vector is equal to a times 1/2, 1. Let's call the vector 1/2, 1 the vector 1, v1. Now looking at the blue line, we see that this is the geometric interpretation of v1. So what does it mean to multiply any scalar a? We saw this also in a previous slide. That just means that we're looking at multiple constant multiples of this vector. Assume that that line is straight. Sorry about that. So it's just a line through the origin that contains the vector v1. We can also consider another interpretation of this solution here. And in doing so, we notice that since we're talking about the combination of any A here times a vector, it's just actually equal to the span of this vector. Or since we've named it V1, we can talk about the span of V1. Now let's look at this linear system and see if it has a non-trivial solution, or does this system have infinitely many solutions? So again, all we need to look at is the coefficient matrix. When performing EROs, putting this matrix into RREF, we notice we have this matrix here, which gives us the solution of x1 is equal to 0 and x2 is equal to 0. Again, that means that our x is equal to the 0 vector, which is our trivial solution. Now let's look at the geometric interpretation of this trivial solution. So if we have x1 equal to 0 and x2 equal to 0 in R2, this is actually just the point at the origin. Our next example asks us to find the solution to this homogeneous linear system. Notice that we have one equation with three unknowns. One might write the coefficient matrix in this form so we can clearly see that we will have two free variables, our x2 and our x3. So clearly we notice here our solution to the system will be x1 is equal to 3x2 plus x3. x2 is a free variable and x3 is a free variable. Now let's let x2 equal a, which is any real number, and x3, we wanted it to equal b. It wants to be a different value because it's not guaranteed that those are the same. So therefore, our solution to the system will look like this. 3a plus 2b, and then we have a and b. So this is the solution to our system. Now let's look at this solution again. We actually now want to write it in parametric vector form. Writing it in parametric vector form, it might be easier for us to look at the system in this way, the vector in this way. The 3a plus 2b, and now we have a plus 0b, which is the a that is here, and then 0a plus b, which represents this b here. Writing this in parametric vector form, we notice that we can split up our vectors into two vectors added together, 3a, a, and 0a, plus 2b, 0b, and b. Now, because we have constants a and b, which can be any real number, we can take those out. So the parametric vector form of this solution would be a times 3, 1, 0, plus b times, I'm running out of space. So let's do that over. Okay, again we have a times the vector 3, 1, 0, and b times the vector 2, 0, 1. Okay? And this again here is our parametric vector form. Now let's look at the geometric interpretation of this solution of x. Let's call the vector 310 v1 and the vector 201 v2. So we have here our vector v1, and we notice it is 3 in the the x1 direction. It goes 1 in the x2 direction, and we do not go up because we don't have a x3 direction. Likewise, we make our v2 vector. In blue, we now see, and excuse my writing, an infinite plane that contains the vectors v1 and v2. So what does that tell us? That anything in this plane, okay, is a solution to this system. And so what is another way that we can write the solution to this system? Again, we can say that this is the span of the vectors 3, 1, 0 and 2, 0, 1, which is also equal to the span of, we've called this v1 and v2, vectors v1 and v2. Now I would like you to write down this problem and solve it in your reading assignment for section 1.5. It should be your last question, number 6. Describe all the solutions to the homogeneous linear system in parametric vector form. And our system is x1 plus 3x2 minus 3x3 plus 7x4 is equal to 0. And x2 minus 4x3 plus 5x4 is equal to 0.